So I'm going to apologize in advance because this is going to be a fairly long section. So if we had an in-person class, it's very likely that this section would take us 2 days of class time. So if you need to pause this halfway, absolutely take the time. It is a lot going on here. So what we're going to talk about are maximum and minimum values. So we've done all of this in Calc 1. You learned how to find local minimum, which corresponded typically to critical numbers or critical values of your function. And then you also learned how to find absolute max and mins. So that was the absolute biggest a function could be, or the absolute smallest on a specific interval. What we want to do now is we want to extend those to functions of two variables. So it has the same kind of concepts as before. The problem is finding critical numbers is more difficult, and for sure finding extreme values is a lot harder. So we're going to take this kind of slow to make sure we really understand everything that's going on. So we're going to start with what is the definition of all of these different things. So we say a function f of xy has a local minimum at the point AB if the function values are going to be greater than or equal to the z value corresponding to that AB. Okay. And this only has to happen nearby the point AB. So remember when you found local maxes and mins, it only had to be in a certain area. It didn't necessarily mean it held true for everything. It was just nearby that point. Then the number, which is the z value corresponding to it, so you would plug in AB to find z. This is called the local min value. So you have a local minimum or maximum, because it would just be the opposite case, occurring at a point if this inequality holds nearby. The actual local min value is the z value corresponding to that point. Okay. When we define absolute max and min, this inequality is going to hold true no matter the value of x and y in your domain. So if the inequality holds true, for all xy in the domain of f, then we say f has an absolute minimum. Or you can also just abbreviate absolute min at the point AB. So absolute is much harder because it has to hold true always. And then we really have the same exact definition for maximum. It's just maximum would mean that the inequality faces the other direction. So you have local maximum and local or absolute maximum as well. So just to add that in, likewise, f of xy has a local max at the point AB if the output of our function is at most f of AB nearby that point. And then if it holds true for all x, y in the domain of your function, it is the absolute maximum, right? So when we went about trying to identify where local max and min occurred, if you remembered in Calc 1, that would happen either when the derivative was 0 or when the derivative was undefined. Here, because we have partial derivatives instead, we're really going to end up having to solve systems of equations. So I still am going to have the same criteria. I want that derivative, those partial derivatives to equal 0, but that point has to make both partials 0 simultaneously. We're not going to consider the case that the partials are undefined because it would be way too complicated, and solving those systems would be something that's beyond our capabilities by hand. You would need a computer software to go through that. So to give you just a visual as to what's going on, if f does have a local max or min, at the point AB, then we're going to be able to say the partial derivative evaluated at that point is 0 for x, and the partial with respect to y evaluated at that point is equal to 0. So picture-wise, what we've got going on here is we've got some surface, and maybe our surface does something like this. It's kind of like a bell-shaped. So this point right here would be the point A, B, and then whatever the z value is corresponding to it. So this is our surface, f of xy. Okay. So this particular point, if you look at the tangent line in the x direction, this will be line 1, and the tangent line in this direction would be L2. Both of those will have a slope of 0. So the points that this happens for, where both partials are 0 simultaneously, these are called critical points. And in the same way, we had a critical point for a function. It was either when the partials or when the derivative was 0 or undefined. Same thing holds here. So we say a point AB is called a critical point of f if and only if the partial derivatives evaluated at AB equals 0, both of these simultaneously, or the partial derivatives at these two do not exist. Okay. Again, we're really only going to be considering this case because this would be very difficult for us to find and evaluate. So in the same way we had a test to determine if something was a local min or a local max, if you remember, that was the first derivative test. So if you had a point right here, A, and you were evaluating this in the derivative, if your derivative was positive on this side and negative on this side, that meant your function was increasing and then decreasing, so you would have a local max. Then, in addition, if it was the opposite, if it was negative to positive, the function was decreasing and then increasing, you had a local min. The other way we could go through and we could test about whether something was a local max or min was with the second derivative test. So if you remember, if the second derivative was negative, what that meant, it was concave down. So the graph of your function would look something like this, and that critical value would correspond to a local max. if the second derivative was positive at that point, that meant it was concave up and you would have a local min. The problem for us is our second derivative, we have a bunch of partials. So it's a little more complicated as to what goes on here. So we still have a test that will help us out, and it is called still our second derivative test. So what this states is, suppose the partial derivatives of f are continuous on a disk with center AB. And suppose that when you plug this point into the partial with respect to x, it equals 0. And the partial with respect to y at this point is 0. So essentially this is stating that the point AB is a critical number of the function. We're going to go ahead and define a function called D, where we're going to input x and y's. And this function D is going to be based on a combination of our second partials. So it is going to be the partial with respect to x twice times the partial with respect to y twice minus that mixed partial squared. Okay. What this actually is the determinant of a 2 by 2 matrix, where you take the partial with respect to x twice, the partial with respect to x then y then x, and then y then y. So remember, when you take the determinant of this 2 by 2 matrix, you would do the product minus the product. And in this case, because it is a function that has continuous partial derivatives, remember Clause's theorem tells us those mixed partials are the same. This is something that's called the Jacobian of this function. If you're going to go on to differential equations, you'll learn about some aspects of this there. And if you're going on to higher level mathematics, the Jacobian is really important for determining stability of stuff. Okay. So what we're going to do is we're going to evaluate this function at our critical number. So all of these partials are going to be evaluated at the point AB. And then depending on the value of D, it's going to tell us what kind of local extrema we have. So based on this, we have 3 possibilities. Okay. The first is if we find out this function evaluated at AB is positive. The only way that can happen is if this product is bigger than this one. Okay. With that, there's then 2 possible cases. Okay. This has to be a positive number in order to make this whole thing positive. The only way that can happen is if these 2 match in sign. So either the 2 partials with respect to x and 2 partials with respect to y are both positive or both negative. So if I plug in this point for D and it's positive, and the partial with respect to x twice evaluated at this point is positive. Okay. Immediately, this tells you that the partial with respect to y at this point would also be positive. So you could test this instead. There's just no reason to test both because this thing has to be a positive quantity to make D overall positive. Because this, you're going to be subtracting something for sure because that thing squared will be positive. So I'm definitely removing something from these first pieces. Okay. So if this evaluated at AB is positive and the partial with respect to x twice is positive, you can think of that as being concave up. So immediately it tells you you have a local minimum. So then the function evaluated at AB is a local min value. Okay. If the opposite happens, if this thing overall is positive and the partial with respect to x twice at that point is negative, immediately again they have to match in sign. That would tell you the partial with respect to y twice also is negative to make this piece positive. Well, if your second derivative is negative, you can think of that as being concave down. So it would have this kind of shape in the x direction. So immediately you have a local maximum instead. So the z value corresponding to AB is a local max value. Okay. Then we have one last case to consider. If this thing is overall negative, that means one of two things. Either these are mismatched in sign, so in one direction you have concave up, the other direction you have concave down. That's kind of a contradictory statement because in one direction it's looking like it's a local max, and the other it's looking like a local min. Or the other possibility is this is more dominant to make this thing overall negative. So your mixed partials are really what's controlling here. And if that's the case, that means they're kind of fighting each other as to what's happening in the x and y direction. So if this thing is negative, then you're not going to have anything going on. It's not a local max or a local min. It's kind of like the case when you were doing your first derivative test and here was your value and it went from increasing to increasing. That point might still be important, but it didn't give us anything significant about that function. So the third and final possibility is if when you plug this value in for AB, it's negative, then the function evaluated at AB is not a local max or min. Okay. So you have to figure out what are your critical numbers. Then you also are going to need your second partials anyway. So you've got to go ahead and find this value of D. Once you find the critical numbers, you plug them into this function that you get, and that's going to go ahead and classify your extrema. So before we get to more complicated examples, I want to start with a function that you've actually seen many, many times before. So this way I can graph what's actually going on here. So the example we're going to begin with is we're going to let f of xy equal y squared minus x squared. So if you remember graphing this function, that had that saddle shape to it. Okay. With this being our function, we're going to determine if f has local max or min values. And if it does, we're going to figure out exactly what those max and min values are. So I need to figure out where my first partial derivative is equals 0, but I'm also going to have to find this function d. So I think it's easiest for you to start by just finding all first and second partials. So if I take the partial with respect to x, that will be negative 2x. And the partial with respect to y is 2y. If I then take the partial with respect to x again, this is negative 2. And the partial with respect to y again is positive 2. And so also, if I take the mixed partial, the derivative of this with respect to y is 0, and the derivative of this with respect to x is 0. So these mixed partials are exactly the same. Okay. So these ones I don't need right now. They're helpful in classifying. I'm really just going to work with these to find any critical points. So again, you are solving a system of equations because you want both of these to equal 0 simultaneously. You need the partial with respect to x to equal 0 and the partial with respect to y. So the system you're solving is when does negative 2x equal 0 and when does 2y equal 0. So this is the nicest system we could possibly have. The only way this will happen is if x is equal to 0 and y is equal to 0. So 0, 0 is my only critical point. And we're going to have to write critical point so many times, we just label it as CP. Okay. Moving on to the second derivative test. I now want to classify this point. So my function d, the reason it's d is because it was the determinant of that matrix, is going to be the two solid partials minus the mixed partial squared. Well, the partial with respect to x twice is negative 2. Partial with respect to y twice is positive 2. And my mixed partial was 0. So this one is very nice because this is just always equal to negative 4. Doesn't end up depending on x and y at all. So when you plug in the critical point, it's negative 4, which is definitely less than 0. So what this means, this is that third case when the determinant is negative. 0, 0 is neither a local max nor min. And really, you can see this just from the picture. So again, this is one that we have graphed in 3 dimensions because it's got that saddle. So in the y direction, it's got this hyperbola opening along the y-axis. But then in the x direction, it has the hyperbola that's falling downward. So this created that saddle shape. Okay. So at the point 0, 0, which is just right there at the origin, in one direction it's climbing, in the other direction it's falling. So although the tangent lines in the x and y direction equal 0 at that point, overall, you can't classify this as a local max or min because it's doing 2 different things around it. So when we have something like this, when you find out that it's neither a local max or min, and the determinant evaluated at this point is less than 0, we call these points saddle points because it looks like it's on a saddle. It's curving up in one direction, curving down in the other. So you're either going to have a local max or min, or you're going to have a saddle point when it's doing neither of those things. So let's try a different example that's going to be a little bit more complicated to find the critical points of, and then we'll go ahead and classify all of those as well. So for this example, we're going to classify any critical points of the function f, which is going to be y cubed plus 3x squared y minus 6x squared minus 6y squared plus 2. So I got to find all of my first and second partials. So I'm going to do that part first. We'll start with the partial with respect to x. So only these have x involved. So the derivative of the first piece would be 6xy. Derivative of the second piece is going to be minus 12x. Then when we go to take the derivative of y, we've got 3 components. So the partial with respect to y is going to be 3y squared plus 3x squared minus 12y. So we got our first partials. Now we can take the second. So we'll start with the partial with respect to x twice. So just differentiating this with respect to x will give us 6y minus 12. If I take the derivative of this with respect to y, it's just these two pieces. It happens to be the same thing, 6y minus 12. Doesn't always happen. It could be something completely different. It's just, in this case, it was. And then finding that mixed partial, again, because we're taking their derivatives, they better be the same. So derivative of this with respect to y will be 6x. And same thing if you took the derivative of this with respect to x, 6x. Okay. So I've got all my partials out of the way. Now I want to go ahead and I want to find my critical points. And so this is again where I'm solving this system where those first partials equal 0. So that means I'm solving 6xy minus 12x equals 0, and 3y squared plus 3x squared minus 12y equals 0. Okay. Both of these I can clean up just a tiny bit to make my life easier, because these constants are both divisible by 6, and then here all of those are divisible by 3. So at least I can make them a little bit nicer. The first equation would be xy minus 2x equals 0. And then that is y squared plus x squared minus 4y equals 0. So I'm going to call this one equation 1 and this one equation 2. So what I need to do are I need to find points that again make both of these 0 simultaneously. So you have to be careful with solving this system of equation. You're probably going to have multiple points. So what I need to do is I need to work with one of the equations. If I tried to find x or y values that made the second one equal to 0, I don't even really know where to begin because none of these have something in common that I can take out. Looking at this first equation, however, both of those have an x in common that I can factor. And then I know what happens if I have the product of two stuff is equal to 0. So I'm going to start with equation 1. We have xy minus 2x needs to equal 0. So factoring out an x gives us x times y minus 2 equals 0. Well, the only way that can happen is if x is equal to 0 or if y equals 2, just from setting each piece equal to 0. So at this point, it might be super natural for you to say, okay, I've got x is 0, y is 0, 0, 2 is a critical point. Although 0, 2 would make this first equation equal 0, if I were to plug that into here, that would be 3 times 2 squared plus 3 times 0 squared minus 12 times 2 equals 0. Well, that's 3 times 4, so that's 12, plus 0 minus 24 is 0. You end up with negative 12 equals 0. Okay? So although that 0.02 would make the first partial equal 0, it does not make the partial with respect to y equals 0. So be super careful. 0, 2 is not a critical point, because if you plug this into the partial with respect to y, it does not equal 0. And I need both of these to equal 0 simultaneously at that point. So the number one mistake that happens is students end up finding more critical points than they need to by just pairing together all of these possibilities. Okay. Instead, I know if x equals 0, the partial with respect to x is 0. What I want to do then is, okay, if x is equal to 0, what does y have to equal to make the second equation equal 0? And then I'm going to do the same thing. I'm going to set y equal to 2 into the second equation and find what x then will make my partial with respect to y equal 0. So I kind of have two subcases to consider now utilizing the second equation. So I'm going to start with the first point for x equaling 0. Okay. Plugging that into equation 2 gives me y squared plus 0 squared minus 4y equals 0. Well, that's just y squared minus 4y equals 0. And then I can go ahead and factor out a y. And this gives me two values, 0 and 4. Okay. So when x equals 0, I have two separate y values that will make it so my partial with respect to y is 0. So I'm going to pair 0 up with each of these. 0, 0 and 0, 4 are critical points. Okay. So I've utilized this part. Now I'm going to do the same thing with y equaling 2 and figure out what does x need to equal. So for y equaling 2, plugging that in up here, that would be 2 squared plus x squared minus 4 times 2 equals 0. That's 4 plus x squared minus 8 is 0, which is x squared minus 4 is 0. And then you could factor this. It's a difference of squares. You can move the 4 over, take a square root, but hopefully at this point you see there's two possibilities, plus or minus 2. So I'm going to pair each of these x's up with this y to figure out my critical points. So this gives me two possibilities, positive 2 and negative 2. So when x is positive 2, y is positive 2. And when x is negative 2, y is positive 2. These are also critical points. So really, I just have 4 critical points. Don't go through and say, now I found all of these values, let me just start pairing everything together. That's not true. That is the #1 most common mistake in these problems. So I want to put that just as a little note because it happens very frequently. The most common mistake is finding too many critical points. And I'm going to put those in parentheses because they're really, and not parentheses, quotation marks, they're not really critical points. They don't make both derivatives equal 0. So the most common mistake is finding too many critical points by finding all xy combinations from solving partial with respect to x equaling 0 and the partial with respect to y equaling 0. Okay, so just be conscientious of that. And again, you can use this as an example, or you can guarantee and test each of these into the partials to make sure you get 0 for both of them. Because it might be natural to say, well, I got y equals 0, and over here I got x equals 2, so 0, 2 is a critical number. But again, it won't make both of these equal 0 at the same time. So you got to take it case by case. Okay? But now that we have all of the critical values, we can go ahead and we can apply our second derivative test. So again, we have our function d, which is the determinant of that Jacobian matrix. It is the partial with respect to x twice, partial with respect to y twice, minus the mixed partial squared. And just going back up to what those were, partial with respect to x and y twice were the same, and then the mixed partial is 6x. So this function d is going to be 6y minus 12 times 6y minus 12 minus 6x squared, which we can clean up to just 6y minus 12 squared, and then minus 36x squared. The other thing I'm just going to write off to the side here so I don't need to keep scrolling up is the partial with respect to x twice is 6y minus 12. Because if d evaluated at the critical point is positive, then I need to plug it into the partial with respect to x twice to see which specific type of extrema it is. So we've got 4 critical points that we have to go through and test. 0, 0, 0, 4, 2, 2, negative 2, 2. So I'm going to start with 0, 0. So plugging this into D is thankfully not bad. This will be negative 12 squared minus 36 times 0 squared, okay, which is really just positive 144. So this is definitely greater than 0. So because of this, I need to figure out which specific case I'm in. So I'm going to plug this into my partial with respect to x twice. And when I do that, that would be 6 times 0 minus 12. So overall, the second partial is negative. And remember, negative you can think of as concave down. So that means this is a local max. If you're asked to find the local max value, then you would just go ahead way back up here and you would plug that into this expression, and the z value is the max value. So thankfully 0, 0 is nice. All of those would be 0. 2 is a local max value. All right, so we got one critical point down. Let's do the next one, which was 0, 4. Plugging this into D will give us 6 times 4, that's 24, minus 12 squared, and then minus 36 times 0 squared. So that gives us positive 12 squared, which is 144. This thing is definitely positive. So I need to figure out then what is going on with this partial. So if I plug 0, 4 in, that would be 6 times 4 minus 12. That's 24 minus 12. This thing is definitely greater than 0. So that indicates you've got concave up. So this is a local min. Okay. 2 more critical numbers to go. The first one being 2, 2. And then the second one is negative 2, positive 2. So starting with the first one, plugging this into D. Again, just going to highlight this so it's easy to see. This would be 6 times 2, which is 12, minus 12 squared, minus 36 times 2 squared. So this really ends up being 0 minus 36 times 4. And I really don't care what number that is. This thing's definitely negative. So this is the case where we kind of have contradictory things going on. And in some directions, it's going up. In other directions, it's going down. So this is a saddle point. One more point to go. Plugging this in. Our y has not changed, so 6 times 2 is 12, minus 12 squared, minus 36 times negative 2 squared. That still just makes it positive, so this ends up being the same thing. Overall, this is negative, so this point is also a saddle point. So we have found and classified all of our critical points. Okay. So if you need a break, this would be a good place to stop because we're going to go on to a different topic because you can see these problems get very, very long. I cannot feasibly give you too many of them. This video is going to be long enough. So I really only have 2 more examples to go through, but these ones are about finding absolute max and min values. And I won't lie, these are a bit harder because again, absolute, it's more complicated. That inequality has to hold true for everything. Luckily enough though, if you remember back in Calc 1, we talked only about finding absolute max and mins on closed intervals. And that was an extreme value theorem that helped us get that. It's going to be the same idea here. I'm going to have a specific region that I'm looking for the extreme values on. So what I want to do first is I want to talk about what does it mean to kind of have a closed interval, but now extended to 2 dimensions. So this is going to be called a closed and bounded set. So we're going to switch and we're going to talk about absolute max and min values. So we say a closed set in R2 is one which contains all its boundary points. And then a bounded set, if you remember the word bounded, it just basically means it won't go on infinitely. So what you can actually do in 2 dimensions is if you have a bounded set, you can always draw a circle around it. So this is a set that is contained in some disk. Okay. So just to give you some examples, if I have a rectangle, something like this, and I'm going to actually make it a little bit smaller. Maybe it's right here. If I can equal these endpoints, or which is basically just the edges of this box, this set is closed and bounded. Because what I can do is I can contain this in a disk. So it's bounded because I can draw a circle around it, and then it's closed because I can equal everything on the edges. However, if I couldn't equal the edge values, so essentially what this would look like is I had a dotted border. That meant I could get very close to it, but I could not equal anything on the edge. This would be bounded, but it is not closed. I want to make sure I can equal all the points on the outer perimeter of whatever shape I'm working with. So when I talk about finding extreme values of a function, meaning the absolute max and absolute min, I'm only going to be able to do this on a closed bounded set. I need to make sure I'm not having one side go off to infinity, and I need to make sure that every point on my boundary I can equal. The way I'm going to do this is very similar to Calc 1, but it is a more thorough process. So if you remember back in Calc 1, what you did was we had, instead of a set like this, we had an interval. If you wanted the extreme values of this function on this interval, you had 2 things you had to do. Okay. You would have to first find all the critical values inside A and B. So like in this example, this would be a critical value. And you would have to find the y value corresponding to that point. Then you needed to check the endpoints as well. And so of those 3 z or y values, the biggest one was your absolute max. The smallest was your absolute min. Okay? So that's what we did back in Calculus 1. But you had to check the endpoints because those could be one of the extrema. So you can see here, this would not be a critical value because my graph is still going downwards. But however, this point is the absolute minimum on that interval. The problem is for us, I can find the stuff inside easily. We can find critical values or critical points. We just did that. But I've got to test my boundary in the same way that I tested these endpoints. So this problem is going to boil down to doing some critical values, and then we're going to have to find the critical values on the boundary too. So it's kind of a 2-for-1 process of you have a Calculus 3 component, and then it's going to boil down as well to a Calculus 1 problem. These will take you quite a while. There is no feasible way you could be asked more than one of these on a test, because these 2 problems alone are probably going to take me about 30 minutes or so to go through. Okay. So I'm going to outline the process first, and then we'll jump into the examples. So our extreme value theorem is what we're using to find the absolute max and min. Same one from Calculus 1. It states if our function of 2 variables is continuous on a closed bounded set D, in R2, then f attains an absolute max and absolute min inside or on D. Okay. So to find these extreme values, we've got a couple things we have to do. The first is we're going to evaluate f at its critical points inside D. So this will give you some possibilities for the absolute max and min. Second thing you're going to do is you're going to find the extreme values of f on D, so on the boundary of D. Okay. And that will give you more possibilities for your extreme values. This is basically going to create a list of numbers. And so your third and final step is from this giant list you get, the largest Z value is the absolute max. The smallest is the absolute min. And as a little note, this step, or step 2, will require parametrizing the boundary. Okay. So we're going to do 2 different examples with 2 types of sets D. One is going to be a circle, and then one is going to be a triangular region. So we'll start with the circle. We want to find the extreme values of the function f, which is 2x cubed plus y to the 4th, on the set D, which is all x and y, such that x squared plus y squared is less than or equal to 1. Okay. So I need to start, I'm going to draw my D. X squared plus y squared equals 1 is the unit circle. So we've got our unit circle of length 1, and so this is set D. One thing you have to verify first is we are using the extreme value theorem. If I go back here, it has to be continuous on a closed bounded set D. I need to verify this is true before I can actually find my extreme values, because I'm only guaranteed extreme values on closed bounded sets with continuous functions. So definitely from here, D is for sure a closed and bounded set. It is a circle. I can contain it in a circle. It's closed because I have less than or equal to 1, so I can equal that outer edge. And then really, this is just a polynomial because it's got x to powers and y's to powers. That is definitely a continuous function. So here, f is a polynomial. So it's definitely continuous on D. So I am guaranteed that it has an absolute max and min somewhere inside the set D. Could be inside the circle or it could be on the circle. So the first thing I want to do is I want to find what are there possibilities for extreme values inside D. So this is where I need to find critical points, and then I need to see what are the z values corresponding to that. So at least I don't have to go through and I don't have to find extra partials or anything like that. I'm just seeing, okay, if this is a critical point, what is the z value associated to it? What we do need to solve is where do these first partials equal 0 simultaneously? Well, if I take the partial with respect to x, that's just this piece, so it ends up being 6x squared. So we need that to equal 0. And then if I take the partial with respect to y, it is just going to be 4y cubed. Okay. The only way both of these equations will be 0, for the first one, I would need x to be 0. For the second, I need to be my y to be 0. So 0, 0 is the only critical point. And that is definitely inside of D. If you found points that were outside, you would not need to test them. It's only the ones inside D. So what I'm going to do is I'm going to find what is the z value corresponding to this. So to just recopy our function, this is 2x cubed plus y to the 4th. So plugging in my critical value, well, they're both 0, so it gives me 0. So what I like to do is I like to highlight these. If you're using paper or pencil, box it. You don't want to lose track of this number because this is a possibility for an extreme value. It could be one of them. It might not end up being. It could be both the things occur on the boundary. Okay. So I found everything inside of D. My second step is to find the extreme values of f on the boundary of d, which in this case is the unit circle. X squared plus y squared equals 1. So what I need to do here is I need to guarantee I'm only searching the boundary, but I am still evaluating this function. So I need to figure out a way to guarantee I'm on the circle of radius 1. And you can hopefully think of an easy way to parameterize this. Use sines and cosines. So here, to guarantee we are only on the boundary of D, we can use a parametric function. So we can define the vector function r of t to be cosine of t, sine of t. And then with that, I only need to go around the circle once, so I can also make restrictions on my t value. If t is between 0 and 2 pi, that will go ahead and trace the entire circle of radius 1 exactly once. Okay? So if I pick these points, it guarantees me I'm on the boundary. What I want to do now is I want to see, okay, well, if my x is going to be cosine of t and my y is going to be sine of t, I can figure out all my z values just on the boundary. So from here, we're going to let g of t be the function f evaluated on the boundary. Okay. So my x is going to get replaced by cosine of t, and my y gets replaced by sine of t, because that restriction guarantees my x and y are on the circle of radius 1, and this tells me what are my z values only on the boundary, the circle of radius 1. So in turn, it gives me a single variable function just dealing with t. Okay. So ultimately this g of t gives the values of f on the boundary of D. Okay. And now I have a single variable function. I know how to find the extreme values of that specifically for these values of t. This is now a calculus 1 problem. So from here, we want to find the extreme values of g on the interval 0 to 2 pi. Okay. So being that Calc 1 problem, I'm going to go ahead and find any critical points that fall inside this range. And then I need to test the endpoints of the boundary as well. So finding those critical points, we go ahead and take a derivative, and we're going to have a bunch of chain rule. So bringing the 3 down gives us 6 cosine squared of t. But then chain rule, you have to take the derivative of cosine, which is negative sine. So I'm going to pop that minus sign out front. Derivative is sine to the 4th. Again, bring the 4 down, because that is the outer function. Decrease the power by 1. And then chain rule, I've got to take the derivative of sine of t. So I get a cosine of t attached. And so I want to see, where does this thing end up equaling 0? Okay. So at least we can do a little bit of factoring out. So we've got -6 and 4 as our constants. I'm going to go ahead and take out a -2. They also both have at least one sine and at least one cosine. So I'm going to factor both of those out as well. So we can take out a cosine of t and a sine of t. From the first piece, we're then left with +3 and a single cosine. From the second piece, we're left with taking out a minus, so we're left with a -2. And then we're taking out one sine and one cosine, so we are left with sine squared of t. Okay. And I want to see, when does this equal 0? So we're going to have this equals 0, this equals 0, and then I'm going to need to set this equal to 0 and solve it. So the problem is solving that trig equation. Now we're going back to trigonometry, or even calculus 2. We did a lot of that there. I've got to find where this thing equals 0. So I need to go ahead and rewrite this entire expression, either all in terms of sines or all in terms of cosines. So the easiest one to use is to just use that Pythagorean identity. We know sine squared plus cosine squared is 1. So what I can do in place of that sine squared is replace it by 1 minus cosine squared. Because this is now going to give me a second degree equation involving cosines instead. Right. So at this point, I can keep factoring from here, but also I could set each piece equal to 0. So I'm going to do that at this point. You can look at my notes if you want to see a different way, but I'm going to set each of them equal to 0. So either cosine of t equals 0, sine of t equals 0, or this expression, which I'll distribute that -2, is equal to 0. Okay. And I'm only looking for t values in between 0 and 2 pi. So for the first one, if cosine equals 0, that happens at 90-degree angles. This means it happens at pi over 2 or 3 pi over 2. If sine of t equals 0 on this interval, that tells us other t critical numbers are 0, pi, and 2 pi. And then this, I got to do more work for still, but that's okay. We'll get to that. What I want to mention here is I end up getting the boundaries as critical numbers. So these are the boundary of the interval 0 to 2. 2 pi. So the boundary of this corresponds to 2 critical numbers. So if it ended up being that those weren't critical numbers, I would have to go back and test the boundary endpoints separately. And you'll see in our next example, that's going to happen. But remember, once I find all of these critical numbers, I've got to plug them in back up here, and it gives me that list for possibilities of my extreme values. Okay. So all 5 of these, I need to plug back into G to get the Z value corresponding to these points. But I still have this one that I have to go about solving. So I'm just going to reflip this in the right order. This is 2 cosine squared of t plus 3 cosine of t minus 2 is 0. And this actually does factor. So you have 2 cosine and then just cosine. And then if I do positive 2 and negative 1, the outer will give me 4 cosine of t minus cosine of t, exactly the correct inner term. So this first one tells you that cosine of t is equal to a half. The second tells you that cosine of t is equal to negative 2. Thankfully here, this is not possible. And then for this one, that would happen at 60-degree angles, so pi over 3. Cosine is positive in quadrant 1, so pi over 3 is a possibility. And then the other place it's positive is in quadrant 4, and that angle would be 5 pi over 3. Right. So my boundary ended up giving me 1, 2, 3, 4, 5, 6, 7 possible extreme values. So I need to plug all of them into G to find the Z value corresponding to it. Because remember, each of these T's corresponds to an XY value, and then that XY value corresponds to a Z. There's just no need for me to figure out what X and Y is and then plug it back into here. This function I've defined G of T gives me the Z values for these T points. So it bypasses needing to find the XY. So since we've got all these, we now plug all of these values of T into the function G of T, which is 2 cosine cubed of T plus sine to the 4th of T, to get possible extreme values. You can say they're even the remaining possible extreme values. Okay. So I'm going to try to do them in order. My smallest is 0. So if I plug in G of 0, cosine of 0 is 1, so that's 2. Sine of 0 is 4, so this gives me 2. And then rinse and repeat the process. I hope you trust that you could go through all of these. If you plug in pi, cosine of pi is negative 1, and sine is 0, so this will be negative 2. And then G of 2 pi, cosine of 2 pi is positive 1, so the first part is 2, and sine is 0. And again, these are the boundary values of t, so I don't need to also evaluate those boundary values. Now I've got more. We've got the pi over 2 angles, so G of pi over 2 will make cosine 0, but sine either 1 or positive 1, but it's sine to the 4th. So both of these will end up being 1. And then if you plug in pi over 3, it's going to give you 1/2, and it's going to give you root 2's over 3's. And then you're raising them to powers, condensing those fractions. I'm going to trust you can plug this in and simplify it. Use a calculator to help you out. This ends up being 13 over 6. And then if you do 5 pi over 3, it will end up also being 13 over 16. So again, I now am going to box these. 0 was a possibility, and all of these are possibilities. So between all of my lists, I now find the smallest and largest outputs. Back up here, I had 0. Well, I definitely have ones that are smaller and bigger. 13 over 6 is like point something. So our third and final step is to find the largest and smallest values. those are the extremes. So the absolute max value is positive 2. The absolute min value is negative 2. If you need to know the points where that occurs, well, it occurs when t is equal to 0. And when t equals 0, that will be at the point 1, 0. And then the absolute min occurs at pi, which again, just going back to the circle, absolute min occurs at negative 1, 0. So these are the extreme values of this particular function solely on the unit circle centered at 0, 0. So you can see a lot of time going into one problem, and it turns into a bunch of different concepts added together. So take your time with these, box your answers that are your possibilities, so this way they don't fall out of place and you don't lose track of them all. But we're going to do one more example so you can see a different possibility, because you might not be able to do what we just did where I could find a single function to parameterize the boundary. If you've got like rigid sides, you're going to have to do something different to figure that out. So let's try this last example. We're going to go ahead and we're going to find the extreme values of the function f, which is x squared plus y squared minus 2x, where D is the closed and bounded triangular region with vertices 2, 0, 0, 2, and 0, negative 2. So first thing I'm going to do is I'm going to find what is this region D, because it just gives me points for my triangle. And they tell me it's closed and bounded, which is nice. I don't have to go through and verify that. So one vertex is at 2, 0, the other vertex 0, 2, and then 0, negative 2. So I get this triangular region. So this is my set D. So definitely bounded, and they told us it was closed, so I can equal the points on the edge here. The one thing I do need is I need continuity on this region, and f is a polynomial. So it's definitely continuous on D. Okay. So I want to start by finding my critical points inside of D. So I need those partials to equal 0. If I take the partial with respect to x, that will be 2x minus 2. Take the partial with respect to y, that is 2y. Okay. Well, the only way that can happen in the first one, you can factor out a 2, and that gives you x minus 1. The only way the first equation equals 0 is if x is 1. And then from here, the only way this equals 0 is if y is equal to 0. So I get a single critical point, 1, 0, and that is definitely inside my region D. So 1, 0 is a critical point inside D. So this gives me a possible extreme value. So I need to go ahead and I need to plug this into the function, which again, just a copy down here, it's x squared plus y squared minus 2x. So plugging in 1 for x, 0 for y, gives us 1 plus 0 minus 2. So one possible extreme value is negative 1. Okay. Now I need to find the critical points on the boundary. And so that means I'm on this triangle with these different vertices. The problem is here, I am not going to be able to come up with a single parametrization. However, because these are just lines forming the boundary, I can do 3 different parametrizations, and I'm going to have to find the maximum for each of those. So this is comprised of 3 lines. We've got the first line, the second line, and the third, or any order that you want to do these in. So I'll call this one line 1. Let's do clockwise. This is line 2, and this is line 3. So when I'm looking at the critical points on the boundary, line 1, line 2, and line 3 form the boundary. So I need to find a parameterization for each one. Thankfully, lines are not so bad. So line 1 is just the y-axis. So this is really just x is equal to 0 here. So it's the line x equals 0, specifically between negative 2 and positive 2. So we can use the vector function. And since I'm going to come up with multiple, I'm going to index this R1 to be line 1. The x coordinate is 0, the y coordinate varies, and that y coordinate is going to vary between negative 2 and positive 2. Okay. So between these values. Okay. Line 2, if I look at this line, the y-intercept is positive 2, and then the slope is negative 1, because you go down 2 to the right 2. So this line would be y is equal to negative x plus 2. And then you can flip-flop it to make it nicer. It's 2 minus x. So here we can use the vector function R2 of t, where my x is t and my y is exactly that expression. And then if I'm thinking about this segment, the x is varying between 0 and 2. And so my t will do the same. Okay. And then finally, we've got line 3. That y-intercept is negative 2, and the slope is up 2 over 2. It is positive 1. So this is the line x minus 2. So we can use the vector function R3 of t, given by our x being t, and our y is t minus 2. And again, for this line, the x varies between 0 and 2. Okay. So what I need to do is I need to figure out what does the function look like on each of these. And then I go ahead and figure out critical values for that. And then I plug it into whatever my expression ends up being to find my possible extrema. The one thing you don't necessarily have to do is you don't need to test the boundaries of each of these intervals. You could also just test the corners of the vertices in the original function because those are extrema. So then I would just have to find the values inside that specific interval. Up to you what you want to do. I don't really have a preference for you. I'm also going to refresh the function down here so we don't have to keep scrolling up. Okay. So I'm going to start with line 1, which is the vector function r1. And it is 0t, where t is between -2 and +2. Okay. So figuring out what the function looks like on this curve, let's call this g of t. For x, we replace it by 0, and for y, we replace it by t. So luckily, this just gives us t squared. Okay. So I want to find the extrema of t squared on the interval -2 to 2. So we're going to find the critical points inside this interval. So we need to find g prime of t, which is 2t. And so the critical points would be where this thing equals 0. So this happens when t equals 0. So I need the z value corresponding to this. So if I plug that into g, it is 0 squared. Tells me 0 is a possible extreme value. So again, I'm going to mark that to keep track of my list because -1 is a possibility. Now 0 is a possibility. Then I've got the critical points inside -2 to 2. I also need the endpoints now. So all I'm going to do is plug both of these into g. So g of 2 is 2 squared, that's 4. And g of -2 is -2 squared, which is also 4. So these are also possible extreme values. Okay. So what this did is it basically tested these two vertices here. So when I go to test line 2, I technically don't need to test this endpoint because it's the same. But just for consistency, I will go about doing that. So now line 2, we have the vector function r2, which is given by t, 2 minus t. And our t is between 0 and 2 on this interval. Okay. So now I need to figure out what does the function look like on this particular curve, and it'll turn into a function of t, so we'll call it h of t. So I'm going to plug these in for x and y. So this is a little more complicated, so we'll go ahead and label this out. So here all my x's are going to get replaced by t, all of my y's are getting replaced by 2 minus t. And my function's back up here. So x squared plus y squared minus 2x. Okay. And then for time's sake, I trust you can FOIL this thing out, group the like pieces. This would simplify to 2t squared minus 6t plus 4. So now that I've got this single variable function, we're going to go ahead and find the critical points inside the interval 0 to 2. So we've got to differentiate this function, which thankfully is a polynomial, so that would be 4t minus 6. Setting that equal to 0 gives you t is 6 over 4, which is 3/2. So I need the z value corresponding to this, so I plug this back into the function h. That'd be 2 times 3/2 squared minus 6 times 3/2 plus 4. And if you plug this all in or actually do it by hand, you should get that this is -1/2. So again, another possibility for an extreme value. Then doing the endpoints of the interval. If I plug in 0, that would be 2 times 0 minus 6 times 0 plus 4, giving us a possibility of 4. And then if I plug in 2, be 2 times 2 squared minus 6 times 2 plus 4. So this will end up equaling 0, because that'd be 8 minus 12 plus 4. So again, possibility for an extreme value. Okay. So we've got 2 of the 3 lines. One last line to go, line 3, which is given by the vector function t minus 2. And then our t is varying between the same values, 0 and 2. So starting out by figuring out the function corresponding to this, let's call it, I don't know, call it k of t. This would be f evaluated at R3. So my x component gets replaced by t, my y component gets replaced by t minus 2. So this would be t squared plus t minus 2 squared minus 2t. And then realistically, if you go back up here, these are the same thing but opposite signs. So when you square it, really ends up being the same expression. So this ultimately will equal the same single variable function. So at this point, you absolutely could go through, take the derivative, find the critical points, and then test the endpoints. However, because these are exactly the same and exactly the same t values, it does not offer you anything new. You're going to get the same critical value inside the interval, and you're going to get the same value when you evaluate it at the endpoints 0 and 2. So there's no need to test this. It doesn't offer us anything new. Okay. So this is exactly the same as L2 with the same bounds. So we won't get any new possible extreme values. So we've got our full comprehensive list. Now I need to go back through to find my absolute max value and my absolute min value. So looking at my list, we have -1. Then over here we've got 4, 0, 4, 0, -1/2. So my smallest value is actually this one back up here, -1. That is my absolute min value. And then the absolute max occurs at a couple of different spots, but the biggest z value we had is 4. Okay, so these are the absolute max and min values of this function on that triangular region. Okay. So take your time with these, try your best. I know they're a lot of work, but again, finding extrema is super important, because if you're dealing with real life situations, these could represent profit. These could represent really even numbers of deaths of people. If you have a function that's kind of calculating that based on some high risk situation, you're always trying to look for absolutes of stuff to either maximize profit, minimize your cost, minimize the environmental impact of something. So this process is important overall for us.